Okay, so when we left off, we were talking about resistance, and we said that the resistance is the protest of the current flowing through a wire or through an object. And we also said that the resistance of an object is what determines how much current will flow through that object for a given voltage. So if you have a given potential difference, then if you divide it by the resistance, what you'll get will be the current. Okay? What we're saying here should sound familiar to you. V divided by R is equal to I. We tend to write it as V equals IR. This is known as Ohm's Law. And you would have seen it in grade 9 science. If we rearrange it for R is equal to V over I, then we see that resistance will be measured in volts per amp. And we rename this. We rename it an ohm. So resistance is measured in ohms, and the symbol for an ohm is the capital omega. Okay, so it looks like this. I always see it as a stick man who's bow-legged and who's bending over, so you can only see his legs, and he's a stick man, so you can't see his butt even. Okay, so this is Ohm's Law, and some of the questions you will be doing will be with Ohm's Law, and they should be pretty straightforward. But I want to go and talk for a few minutes about the resistance in a wire or in a material. Resistance in wire or other material. So what you're creating your circuit with. Because sometimes we think of the resistance in a microwave, in a light, etc. But we forget about the fact that all the wires that are connecting the light and the microwave have resistance too. And so what are the things that the resistance in our wire is dependent on? Well, remember I had said earlier, think of resistance as friction. So one of the things that how big the resistance in a wire is dependent on is the length of the wire, right? The length of the path that the current has to take. The longer the path of the current, the more resistance there's going to be. Just like if it was friction, right? The longer you push, like, you could push something straight across the floor, or you could zigzag it. But if you zigzag it, you're going to be losing a lot more energy to friction. So when you're building a circuit, you want to use the shortest amount of wires possible. You don't want the wire to loop up around your television and over the lamp and back down to the floor. You want it the shortest amount of wire possible so you're not losing any energy to the resistance of the wire. So the longer the wire, the bigger the resistance. The second thing that it's dependent on is what's called the cross-sectional area. And now the cross-sectional area of a wire is if you take a wire, the cross-sectional area is this end. So it's like how big the wire is in its cross-section, right? Dependent on the diameter or the radius of the wire. Now, there's a name when you go to buy wire, which I didn't know the first time I went to buy it. There's something that's called the gauge of the wire. And when you go to buy wire, then they'll say, what gauge do you want? Take it from me. I'm 100% positive of this. And so it's connected to the cross-sectional area. And there's another chart in your book. I'm just looking for where it is. It's somewhere around 7. There it is, 706. There's a chart that shows gauges of a wire. Now, the surprising thing for me when I first learned about gauges of a wire was probably first year university or something, and had to leave the hardware store and go, I needed wire to do some lab, and so I went to buy it, and Buddy said, what gauge do you want? I was like, So I went back to my dorm room because there were no cell phones then, and I called my father, and I said, okay, tell me about gauge. So the smaller the gauge, the bigger the diameter. And the bigger the gauge, the smaller the diameter. Okay, so it does, so if you say 14 gauge, it has a diameter of 1.63 millimeters, whereas 22 gauge only has a diameter of 0.64 millimeters. So as the gauge of the wire goes up, the diameter goes down. Okay? So why is the cross-sectional, and then from the diameter you could get the cross-sectional area. If you think about the current flowing as if it were water flowing through a pipe, then the narrower the gauge, the narrower the diameter, the narrower the wire, the more the water is going to rub against the sides. The bigger the diameter, then the more the current can flow without rubbing as much, right? Just like the more water could flow through there. So the bigger the diameter, the smaller the resistance. Remember, so this is cross-sectional area. It's A. And most wires are circular, so it would be A equals pi r squared. That's the area of a circle. So in a question, if it tells you the gauge, you'll go to that chart there, and you'll look for the diameter. You never use the third column in the chart. So you look up the diameter, and it's going to give you the diameter in millimeters. So you need to do two things with it. You need to change it to meters, and then you need to cut it in half, because the equation for area asks for radius. Okay? So when you're doing these questions, make sure you change the millimeters to meters and you divide the diameter by 2. Okay, so that's the second thing that resistance in a wire or other material depends on. There's 4 altogether. Number 3 is the material itself. It kind of goes back to, is it a conductor or an insulator, right? It's connected to how well it holds its electrons or not. This thing is called the resistivity. There is a measure of how well a material holds its electrons and therefore how much resistance it has, and its property is called resistivity. Okay? And I'll show you, it's kind of like the coefficient of friction. The bigger the resistivity, the more resistance. The smaller the resistivity, the less. Just like the bigger the mu, the more friction. And the fourth factor, before we go to the equation and a chart in your book, the fourth factor is temperature. If you think about what rooms are air conditioned at school, they're the computer rooms. Metals do not do well at high temperature. The higher the temperature of a metal, the more resistance it has. Strangely enough, maybe, the higher the temperature of a non-metal, an insulator, the better conductor it becomes. If we think about the metals, remember temperature is just a measure of the movement of the electrons, the kinetic energy of the electrons. So the higher the temperature, the faster those electrons inside the metal are moving, and the more they're going to interfere with the flow of the current through. Whereas for an insulator, the higher the temperature, it kind of lets the atoms loosen their grip on their electrons and loosen up a little so that the current can flow through it. So at high temperatures, metals become worse conductors, but insulators become better. It's why if you've ever lived in a big family like me, your toaster will like buzz after you used it a few times because it's getting too hot and it can't operate as well anymore. Okay, there's another chart in your textbook, same page as the gauge. So here's the gauge up here, and remember I said you're going to use the first 2 columns, not the third one. The other chart is down here, and it's showing the resistivity of the conductors. So if it tells you the material is silver, then you go over here and you get that constant for that. So just like if it was a coefficient, okay, it's resistivity, and you would look it up here in this chart. Okay, and so our equation to calculate the resistance of a material is R is equal to rho L over A. And the rho is that resistivity that you're going to look up in the chart. Okay, and it's in ohm meters. This is the length of the wire. It will be in meters. And this is the cross-sectional area, and it will be in meters squared. So in the end, ohm meters times meters divided by meters squared, you'll end up with resistance. Okay, so when you're using this equation, you're going to need the charts. They're on page 706 in your textbook. Okay, So you'll have that equation and Ohm's law for today's practice.